Alright, here I will prove a statement relating convergent sequences with the notion of continuity. So this is, I guess, a theorem defined in metric spaces. So let's write down this statement. So let f from x to y be a function between metric spaces. And we're going to let x be an element of the metric space x. And the statement says that then the function f is continuous at the point x if and only if for all sequences xn that converge to the point x, the sequence f of xn converges to f of x. Okay. So it's a biconditional statement. So to prove this, we have to prove both directions. So let's start with the forward direction first. Okay. So what we want to do is, so we're going this way. So we want to suppose that f is continuous at the point x. So suppose our function f is continuous at the point x. And now we want to take these sequences here. So let xn be a sequence converging to x in the metric space x. And for simplicity, we're going to let y equal f of x. And to be able to use the result about continuity, we can take epsilon to be, I'll write it like this, greater than 0. And then because f is continuous at the point x, then there exists delta greater than 0 such that continuity says that if x prime is an element of the ball of radius delta around the point x, then f of x prime is an element of the ball of radius epsilon around y, because y is f of x. So we have this. So also, so we know xn converges to the point x. So also since xn goes to x in x, so because we have a convergent sequence, there's an epsilon ball that could be centered around the point it converges to, and there's going to be infinitely many points that fit inside that ball. So since xn goes to x in x, given there will be a series of points that squish after a certain point inside that ball. So given a delta, so we're going to take this delta as above, right? Because we have that there, since f is continuous at x, we have that there exists this delta. We'll take this delta, given delta as above. So now we'll state that there exists some point n in the natural numbers, so some index n, such that all these xn's after a certain point live inside the ball of radius delta around the point x. Okay. And because we have this result from the continuity of f, so if some point lives inside the ball of radius delta around x, then straight away you get that f of x, or f of x prime lives inside the ball of radius epsilon around y. So we get that f of xn lives inside ball of radius epsilon around y for all n greater than n. And we want to show this. This is the point, and that's pretty much what we have already. So if f of xn lives inside this ball, then that's basically the definition of converging to the point f of x, because y is f of x. And we're done with this direction of the proof. Now we'll go the other direction. So we want to assume this. So suppose that for all xn going to x, f of xn goes to f of x. Okay. And we're going to prove this by contradiction. So we want to show that f is continuous. To use the method of contradiction, we assume that f is not continuous. Right? Okay, so suppose f is not continuous, then there exists an epsilon positive such that for all delta positive, so if f is not continuous, then we take the complement of the ball of radius epsilon of f of x inside f of the ball of radius delta around x, and we're saying that that's non-empty, right? Okay, so f of ball radius delta around x epsilon that's not empty. So this implies that, well, for all n, so we can take n to be some integer greater than or equal to 1. What we can do, because we have this result, so we can take, so this works for so delta, we let that equal 1 over n, and we get some point in the sequence xn inside the ball of radius delta, which is 1 over n, around x, such that, well, if we take this, it's not going, so f of xn, that particular xn, won't be an element of the ball of radius epsilon around f of x, because we have this result, such that f of xn is not an element of the ball radius epsilon around f of x. Okay. So from this statement we get, so here we're basically saying that xn, the sequence xn, converges to x, right? Because it's 1 over n if it's inside this ball, and so the sequence xn will converge to the point x where the ball is centered at. And remember, we want to get a contradiction. Xn goes to x, but, well, f of xn does not converge, or the sequence of f of xn does not converge to f of x, right? Because it's not inside this ball of radius epsilon. So, but the sequence of f of xn does not, I don't know if this is a legitimate, this is legitimate notation, but I'm going to use it anyway, does not converge to f of x. And, well, we've supposed that here, right? Well, let's see here, we've supposed that here, and we have a contradiction immediately. So our assumption that f is not continuous is contradicted. So therefore f is continuous. or I should have said at, is not continuous at the point x. Yeah. F is continuous at x.